We should get started. We have enough of an audience to get going. So welcome back, everyone, to 2021. Hopefully, given the standards or the bar set by 2020, hopefully 2021 will be better. At least it looks like that. So our first speaker today is Yusufcan. Yusufcan Masatlioglu. He is a professor of economics at University of Maryland. He's published in all the top theory journals. He's the editor of Mathematical Social Sciences. And well, his work in decision theory is very well known. I don't think he needs more of an introduction than that. He has agreed that he will take questions as we go along. So ask questions as you like. And as usual, we have 1 hour. The floor is yours.
First of all, thank you for Sudipta's kind words. Again, I'm so sorry for the last time. It was completely my fault again, and I'm really happy to be here. Today, as Sudipta said, whenever you have a question, just shoot it. I'll try to answer as much as I can. Today, I'm going to talk about random choice. It's called a progressive random choice. It's actually co-authored with Emel Filizözbay. Actually, I have known her for a long time, and now we are colleague at Maryland. So what is we try to do in this paper? In general, in economics, actually, we like to sort people. And when we sort people in terms of productivity or in terms of risk preference or taste for the public goods, time preference, you can think of many different ones. And there is one characteristics, and people somehow order in that characteristic. That's what we try to do in generally. So the same thing that I want to do today here, you can think of the one-dimensional heterogeneity. So think about the risk preference. So I have those 5 guys in the slide. Those 5 guys, the light blue guys, you can think of risk, risk neutral. When it goes move towards the right, it gets more risk averse. Okay, so that's what I'm trying to think the underlying model. So there is one thing that I'm interested, and I'm talking about the risk preferences, but it could be anything. Actually, that's exactly what I want to do. Especially the recent development in behavioral economics, we start, studying different things like a limited attention, or loss aversion, or willpower, temptation. And what I'm trying to understand, you fix the model, and there is one parameter that I'm interested in, and I want to order people in terms of that parameter. It could be limited attention. It could be, as I said, willpower, and that's what I would like to do. Okay, so that's the aim of this paper. The problem is, I don't observe people's type, and I don't observe what are the probabilities that types in the society. What I observe as a decision theorist, only their aggregate choices. And in this slide, actually, S is the decision problem they face. I don't observe in this black box because these are the order types, but what I observe, what they choose. As a decision theorist, our aim is actually try to reveal how they ordered and what are the proportions of this, each individual, each type. Okay, so that's the aim. So the rule of the approach, I don't observe those one-dimensional heterogeneity. I know there is a one-dimensional heterogeneity, and you will give me the choices, and I'm going to try to infer types and also the probability distribution over those types. Okay, so that's the important part. So, of course, this is not the first time that people try to do this type of things. There's a well-known model called random utility model. Random utility model more or less do this kind of a similar thing. Again, in the black box, there are a bunch of guys, And again, only observe your choices.
Yusuf?
And the choice actually.
Yusuf, so okay, just one question. So you are interested in both revealing how many types you have or what types you have, plus probability distributions, 2 dimensions, correct?
Exactly.
Okay.
Exactly. I need 2 types of information.
Mm-hmm.
This one type, type of heterogeneity, and also how frequently those types available in the economy.
Another clarifying question, Yusuf. What exactly, I can wait till the model. What exactly is your data? I mean, what exactly you are observing?
So the data here is this pi.
Yes.
This is a stochastic, the probabilistic choice for every budget set S. It will tell me how frequently X is chosen, or Y is chosen, or Z is chosen.
I see. I see. The frequencies. Okay.
Frequencies. Yeah, I need to have a frequencies. How often that alternative is chosen, given a decision problem S.
Okay. Thank you.
Okay. So random utility model is actually a very well-known model. So according to this model, there are individuals, and each individual actually has a preference. This, this preference relation, and there is a mu tells you how, the probability distribution of all these preferences. And the model says that the probability of X chosen in S decided by, tell me all the guys that choose X as their best choice, and you just sum those probabilities, and then it will give you the how you choose X, how frequently you choose X in S. Okay. Actually, random utility model, I'm talking about like a population, but you could also think about this as a single individual has different moods, or the different type of, the day of the time that they have a preference, that they have a changing preference, basically. And the random utilities across to many fields actually use, and very, very successful here. So now what I'm going to tell you, actually, I cannot use random utility in this paper. Why I cannot use it? Because the random utility assumes that each type is rational. So their choices needs to be characterized by a preference relation. Remember, my whole approach is I'm trying to study these behavioral models, limited attention, temptation, all these things. You might actually find people behaving not rationally, or at least their choices is not going to be represented by weak axiom of revealed preference. So that's why I cannot use RUM. The second reason I cannot use RUM, because heterogeneity in RUM could be very, wide. Remember, all I care is a one-dimensional heterogeneity that I care. Okay, so that's the first part that I'm trying to give you a model that satisfies these 2 properties, allow individual behave or violating the world, but underlying model only interested in one-dimensional heterogeneity. Okay, so why I cared actually dropping a preference assumption? Because of this reason. I want to study limited attention. I want to study willpower, satisfying reference dependent social preferences. What is the one-dimensional in each one? Limited attention, whether people are less attentive or more attentive. Less willpower, more willpower. So these are the type of the one-dimensional that I care. So what I'm going to do, actually, I'm just going to give you a very simple example to motivate why I need to drop preference assumption. So let's start with the limited attention. So think about, these are group of individual, or the same individual has different attention properties. Like when you have a good sleep, you are more attentive. When you have less sleep, you are less attentive. So, and the guy from the left to right, their attentiveness increasing when I move left to right. In my simple example, I'm going to take very simple 3-object case. And let's say that we know the preferences, X better than Y, Y better than Z. And alternatives are listed as in Google. And for some reason, Y is actually listed first, Z is the second, and X is the last. So I have 3 types in this example.
Yusuf, the preference X is better than Y and Y is better than Z. For whom is the preference? So is this some...
So I'm going to assume that this is the same across these individuals.
I see, okay.
Because what I want to change only one thing, which is their attentions.
I see. Okay.
I want to keep the preference fixed across, only change the attention.
I see. So all the agents agree on the preference, right?
All they agree, yeah. You can think of this is the cheapest. They are trying to find the cheapest.
Okay.
The first guy is only consider the first alternative he sees. So you can think of this is the guy that go to the supermarket with 3 kids. So he has no time. He's going to grab whatever he sees first. The second guy is actually, he can look at the first 2 objects. And the last guy can look at the entire thing, whatever is available. Okay, so the very dark blue guy is actually fully attentive. And the first guy is very less attentive. So now I want to look at their choices. Okay, so that's what I'm going to construct right now. On the left-hand side, I put all the possible budget sets. There are 4 different, either they can see, all of them available, or only X, Y is available, and similarly the rest. Low attentive guy only sees the first item. If Y is available, he's going to see Y. But if it's not Y is available, he's going to see the Z. Okay, so this is the low attentive guy. So this is his consideration set. There are other alternatives available, but he don't see that. And his choices, in this case, because he only considered one alternative, his choices will be exactly what he pays attention to. If everything is available, he's going to look at the first item and he's going to choose the first item. Okay? So this is very simple. This guy choosing whatever he sees. The second guy consider first 2. So if everything is available, he's going to consider Y, Z. If the budget set X, Y, he's going to consider X, Y. All the binaries actually is full attentive. What he's going to choose now, according to his preferences, he's going to choose the best alternative given his for example, from YZ, he chooses Y. From XY, he chooses X. Okay, so these are his choices. And what about the full attentive guy? He's going to see everything, and he's going to choose exactly according to his preferences. He's going to choose first X. Whenever is X available, he's going to choose X. Otherwise, he's going to choose Y. So
I'm going to just repeat Adam's question. So what you are doing is changing the set of alternatives in some sense, not the way we choose. I mean, given your middle part of this table, given the attention set as my new set of alternatives, all of us use the same ranking, and we are not behavioral in that step. So the quote-unquote behavioral thing comes from changing the set of alternatives, right?
Exactly. The attention part is the behavioral part.
Yeah.
If the attention, no problem, you're a standard guy.
Yeah.
But the issue is your attention. And what I want to order all this, the guys in my population according to their attention. Of course, if their preference is changing, then that's a completely different problem. What I'm interested in is the same individual, but a different attention capacity. You can think that.
And Yusuf, inattention is here defined as I'm overlooking some alternative, right?
That's correct.
Okay.
That's correct. Some of the things. Again, this is just an example. to illustrate what does it mean, the one dimension. Here, the one dimension refers to your attention capacity. You can think that way, but the rest is the same among those individuals.
Another kind of silly question: how does it compare to with your old paper on status quo? So with status quo bias, didn't you start with something similar?
In that model, everything was deterministic.
I see.
And there was only one single individual.
Okay.
Yusuf, another stupid question. Here I have some violation of irrelevant alternatives or something like that, right? Or
exactly. So that's why I said I cannot use random utility. That's actually my next slide.
I see. Okay.
So look at the second type. Second type cannot be represented by a preference. First type and the first and the last type actually can be represented by a preference. Even though it is not that it is preference, it can be represented, but the second type cannot be represented. So that's why the random utility is not good for me. It might be a great model, but it does not serve for my purpose. Okay, so this example that I'm trying to tell you that's why I need something new. I mean, if everybody agree on this, I'm gonna just say that look, that's why I'm gonna change random utility. I mean, there is an obvious change. So I can keep everything except instead of using a preferences, now I'm gonna use a choice function. And the model says that, look, probability of X is being chosen, it's basically, I'm going to look at each type, and whenever X is chosen for that type, and I'm just going to aggregate their frequencies in the population. Okay? And I'm going to call this, instead of a random utility model, I'm going to call it a random choice model. But again, this is not good enough for me because the types are not one-dimensional. The individual here could be any, so they are not ordered in a sense. So the next step, I need to convince you that there is a reasonable way to order these guys.
I have another question. So having said that, these violations, they might be different effects. So I just would like to be sure why, how could you convince me that this is indeed driven by inattention?
I don't know. I have no clue whether it's driven from attention, but I'm gonna say that, look, this guy is coming from attention. That's the story that I tell you.
Sure.
But I cannot use RUM to model these individuals. So all I'm saying is the limitation of the random utility models.
Okay.
So, Yusufcan, I mean, is it not true that any other model, whether it is inattention or willpower or whatever, as long as it will generate this, all you are claiming is that random utility model will not work. It doesn't have to be inattention. It can be anything else.
Exactly. So this is just an example for you to say that the random utility is not, general enough for me to work with. Okay. And actually, I don't care whether attention. I want the model applied to all the other things too. Attention is just the one story that I'm gonna convince you that I need something new. So the second one, I have choice functions, but I want to order them so that I can study this one-dimensional heterogeneity that I'm interested in. How can I actually order choice functions? It might be actually straightforward for you. It wasn't straightforward for me. and I write examples to understand how can I order things. So this is another example that I'm going to use actually to motivate how we can order this. I'm using a paper by Dillenberger and Sadowski. Actually, it's a very cool paper. It's called Ashamed to be Selfish. Very catchy title and a very cool paper. So this paper actually gives the following model. There's a utility function that people trying to maximize. But this guy is actually non-standard because he also cares somehow social norm. He wants, if there is no social norm, he would have been very happy. But if he chooses something away from the social norm, he actually needs to pay a kind of a cost, kind of a utility cost. There is this parameter S. It represents a shame parameter. The higher it is, you care social norm more. Okay. And what I'm going to do actually, I'm going to assume U and social utility and the social norm fixed. All I care is actually this parameter, shame parameter. I'm going to change this shame parameter to see that, how this guy is going to be ordered. Okay, so that's what so the one-dimensional thing that I'm caring right now, this shame parameter. So here's the example. Trust me, I hope that I did everything is right. So I take the utility, X is the best, Y is the second, and Z is the worst. And in terms of shame, in terms of social norm, is the opposite. Z is the the social norm dictate that Z should be chosen, but he likes actually X. So in this table, actually, I created 5 types, and their types actually the shame parameter start with 0. This means that he doesn't care social norm, and then it becomes more and more. He starts caring more and more. And I, created their choices. Okay. So in a sense, they're ordered. Is that right? They're ordered in terms of the shame parameter that I'm interested in. Actually, if you pay attention, let's fix the choice problem, the X, Y, Z. What happens? Type starts choosing X first, then they switch to Y, then they switch to Z. So they follow this order, X, Y, and Z. Let me look at another choice problem, like X, Y. It started with X and switched to Y. And you see that actually all the switching follows the same order. It always, starts with X, switch to Y, and switch to Z. That's the rule that I'm going to call this that they are ordered. There is some kind of underlying order, and the types is ordered according to that ordering. So in this case, actually, I'm going to call the reference ordering. In this case, actually, Z, Y, and X in that order. And for any, if you compare any 2 types, their choices, follows this order. And each type actually becoming more in line with this order. Look at the type 5. Type 5 actually choose as if they have the preference of this order. That's what I'm going to call it. These guys are ordered. Okay, so that will be my definition.
So you're saying you are. Sorry.
Sure.
I'm just thinking. So you want to find when they are going to be ordered like this, is it? I mean, given
exactly.
the data set, you want to tell us whether or when the types can be ordered. Exactly.
That's exactly the. So this is my assumption. I'm going to say that this is the one-dimensional heterogeneity that I mean, and I'm going to look at the data, and I'm going to tell you when you can order these guys accordingly, such a types.
Okay. Okay.
Yes, exactly. That's the game of the, name of the game.
Mm-hmm.
So this is formal definition. If you give me a collection of choice functions, I'm going to call them progressive or ordered with respect to this reference ordering. If I can sort them, that the later types actually more in line with the reference ordering than the earlier types. This is for each S. And that's actually important. The reference ordering applies for each decision problem. So far, so good? Actually, it turns out that this is nothing but single crossing preferences. Mm-hmm. So if my choice functions are derived from a preference relation, this definition exactly single crossing preferences condition. So it is not something new actually. All I did, our intuition that single crossing preferences, I apply to choice functions. And actually, this type of things recently applied by Apastogoya, Balaster, and Lu in an econometrical paper for only for random utility. So the one-dimensional random utility is already done. But since I'm interested in more behavioral things, I need to get out of the random utility world. So that's why we are doing this. Okay. So this progressive is not something that actually we created. It's already there. We just apply the choice functions. So the key thing is actually what is that reference ordering that we are using? There might be very different things could be reference ordering. So here I write a bunch of examples that it could be preferences, or it could be social norm. There are some examples. It could be a salience of a product, or it could be a temptation utility. So it could be anything. So in the first part of the paper, I'm going to assume this reference ordering is exogenously given. Mm-hmm. Okay, so we know that reference ordering, like a social norm. I know what the social norm is, what people actually like. In terms of preferences, you can think of, that common preferences. People try to choose the cheapest option. Okay, and later on, I'm gonna try to convince you that you could endogenize. Okay, so first, let me give you something that it is not progressive. So here actually there are 3 alternatives and there are 6 types. So this is actually, each type is actually coming from the preference maximization. And what I'm going to convince you that this is not a progressive structure, because look at the first one. This individual actually order first choosing Z, then switch to Y, and switch to X. But when we look at the second one, it starts from Y, switch to X, but then it switch back to Y. That cannot be progressive. Okay, so this is where the progressive is violated. Also here, it first start with Y, Z, switch to Y, but then it switch back to Z.
So you cannot have sort of cycles, right? Or
yeah, there will be cycles here. So the progressive structure said you cannot have cycles.
That's right. That's right.
Okay. So in this case, what we could do, we can eliminate actually this one and this one, then it becomes a progressive. Mm-hmm. Okay. So let me erase those things. No, I don't need to erase. Okay, here is the model. And I'm going to call this model as a progressive random choice. So each individual types allowed to have a choice function rather than preference. But what is important here, there will be ordered.
Sorry, Yusuf, one question. So typically this, for instance, this single crossing property, we use it because this is actually the necessary condition to get true revelation of types, for instance, in signaling games. So here plays it actually the same role, correct?
Yes, yes, that's how we are going to use it too.
Okay.
So, but the funny thing is, one is in game theory, the other one is in the decision theory.
No, yeah, yes, I understand. But you know,
but
yes,
it's using the same kind of a way that is going to be used.
Yes. You need some structure on the preferences of individuals to get the to get a scheme that you get that you can reveal the truth.
Yes, exactly. Okay, so this is the model, and that's what we call the progressive random choice. Now the question is, what are the axioms we need on the data such that we can always write your behavior as a this ordered structure? Do you have any guess?
Yes.
Actually, first of all, some evidence. So the first question is, do we have any evidence that people actually order such a ways? Actually, it's very difficult to find the evidence, but the Manzini and Moriarty actually created a unique data set that, first of all, people actually do not use preferences, they use choices. And when you look at their choice types, actually they are progressive. That was actually very surprising for us. I'm sure that, such thing exists, but I was, worried that nobody actually collects such a data. But it is actually, it seems that there is the data. So the first result says, give me the reference ordering. Then it says, every stochastic choice will have a PRC representation with respect to that ordering. So this means that no matter what data you create and what the reference ordering you give me, I can actually create a PRC representation for that data. Having said that, representation actually that I'm going to give is going to be unique. What does it mean? The types are unique and the frequencies also unique.
How unique? Also with respect, also it's ordinally unique, right?
I'm giving you choice functions. So this means that there's no definition ordinal. It tells you what you choose.
Sure. Okay.
In terms of probabilities,
it's unique.
They need to add up to 1. I give you exact number. I'll tell you 33% type 1. Okay. So I want to spend a little bit time. I want to call this a theorem 0, not the theorem 1. Why the theorem 0? Because this is the theorem of everything. It explains any data. Of course, if I'm a psychologist, I would be so happy.
Yusuf, I'm surprised that you get uniqueness for probability because you have finite setup. So I would expect that you have some degree of freedoms, that.
I was surprised too. I'm glad that you are also surprised.
Okay.
Because random utility, random utility is not, their representation is not unique.
Exactly.
Neither preferences nor distributions are unique in the random utility world.
So what's here the driving force for the uniqueness?
Progressive structure.
Progressive structure.
Progressive structure, even though I allow much more general choice functions than the preferences. So this, for example, with 3 alternatives, you have only 6 preference type. But if you focus on the choices, there are 24 choice types.
I see.
So the degree of freedom is much larger in this world. But I add this progressive structure. this progressive structure is strong enough that it reduces the, the number of possible things that it allows a unique representation.
This is interesting.
So the identification actually is very interesting. Why very interesting? Because any model the submodel of progressive random choice that you are going to study, you know that your representation is going to be unique. So I proved for you. For any paper after this, whenever you work on the specific case, your uniqueness is given. But having said that, as of now, I don't have enough structure to get the prediction power.
I understand.
And as an economist, we like prediction power. As I said, if I was a psychologist, I would be so happy. Whatever the data you give me, I can explain it. And I explain it in a unique way.
Sure.
But I'm an economist and I want more than this. But I want to highlight that actually, usually I wouldn't write this theorem if uniqueness is not there. But the uniqueness actually is the interesting thing and it's going to be very important for me.
Absolutely.
Okay? So what could we do to increase our prediction power? I give you all these examples: limited willpower, the limited attention, satisficing. These are all examples of this world. But now what I'm going to do actually, I'm going to focus on one phenomena that I want to study. This allows me, introduce more restrictions, and then I will be able to give you, prediction power. And for this one, actually, what I'm going to call actually less is more. That's what I'm going to focus on, this type of choice types. And I'm going to try to increase our prediction power. So what is less is more? There's actually huge literature on this. I don't know whether if you heard of jam experiments, whether people offer only 6 options, they make a choice easily than when they offer 30, the options with 30 items. And it has been shown that people actually start making more mistakes on the larger sets than in the smaller sets. So people actually find their best options in the smaller set than the larger sets. This basically says that your choice is actually more in line with your original preferences in smaller sets rather than the larger sets. So for this, assume that the reference ordering actually is going to be your preference. That's the kind of underlying assumption that I'm going to stick to it. Okay. So that's the phenomenon that I want to study, and this actually puts constraint on the which choice functions that I can actually choose. So remember our original one. So assume that reference ordering X better than Y better than Z, and look at each choice is actually, this guy is choosing Y in this larger sets, and there is a choice reversal. In a smaller set, he chooses X. But actually, he moves in the right direction. He chooses better options for himself. If this was, for example, if this was Z, I don't want that. Because he was originally choosing Y, but in a smaller set, he's actually choose something that works for him. So I want to actually eliminate this type of behavior. I want to say that if, so this actually, I need to have a condition here. T is a subset of S. That actually I forgot. This says that for a fixed type, if you fix the type T, and this guy actually choose something in a larger set that available in a smaller set, this means that the choices in the smaller set must be better than the choices in the larger set. With Z, this is not satisfied, but for this, if you have a preferences, you will need to satisfy this property. But if the choice functions, some choice function can be violated. Is that clear, the first condition?
Yes,
this is like a
some sort of consistency, right? That if the set T is smaller, then I have to preserve my previous choices, right? Or
either preserve or improve.
Or improve, or even yes.
From Y
I
to
have
X,
to be at least as good as for the largest.
Exactly, at least as good as.
Yes.
You cannot make more mistakes in the smaller set.
Yes.
Okay, so that's exactly the first condition says. Second condition actually is sometimes people make very weird mistakes. Like he chooses Y, but in a subset he never chooses Y. So this is actually called in the decision theory literature is that called a difficult choice, and I don't want that either. So I put two conditions. One is the smaller choices represent your preference more, and on top of this, if you didn't choose X in any smaller set, you will not choose these guys all of a sudden in the bigger sets. Okay, so these two conditions that I'm gonna keep, and I'm gonna say that look, if you satisfy these two conditions, that the collection of choice functions satisfies less is more. And again, with respect to the preference relation, because I use that preference relation here.
But Yusuf, now stupid question, how is it related? Because it's a little bit counter to this preference for flexibility, right?
No, it allows preference for flexibility, but it restricts.
I see.
It still allows, but it does not allow those crazy things. Like when everything is available, you choose your best option. But when there's, the set gets smaller, you start making mistakes.
I see. So basically, I allow for flexibility, but I require that you recognize how can you improve, so to say, right? For the more precise sets, right?
Exactly. And notice that less is more is a condition about types. The progressive condition was about the order across types.
Yes.
So less is more is about each individual in my population.
Yes, for everyone.
I don't want those crazy guys that changing the preferences so drastically.
Yes.
I mean, like a preference assumption is actually such an assumption already. Random utility puts the warp assumption. And instead of warp, I'm putting, less assumption in that sense.
Yes.
And there is no innovation here in terms of name. We called it less is more progressive choice, L-PRC. The first bullet point is the same. There is a probability distribution of those choice functions, and the choices will be written in this formula. The support needs to be progressive. That's the PRC part. And now the second part is the less is more. The support of that mu got to satisfy less is more. Some of the crazy choice function is no longer allowed. I mean, I'm saying crazy, but a given model, they are crazy. For some other model, you might want to use that. Again, this is just the illustration how we can use this PRC model. I'm sure that people are going to, try to put other conditions. I'm just going to show you that, look, this one is enough to get a prediction. Okay, so here again, a collection of choice functions. Indeed, they're progressive in terms of order is you start from Z, switch to Y, and switch to X. But they do not satisfy less is more. Why? Because he choosing Y in the upper set, but in the smaller set, he switched to Z. He actually worse off by going a smaller supermarket.
Yes.
That is crazy because he could have find his better option, in a bigger supermarket, but in a smaller supermarket, he cannot find his good option. Okay. Of course, if you get rid of them, then you will have both progressive and less is more. Okay. What happened? These are not this. Okay. My slides actually all over the place. Characterization. So what are the conditions on the data that it will tell you this is less is more? Actually, this is the a known condition in stochastic choice. What it says, if you if you take two sets, one is bigger, one is smaller, then the probability choosing X actually cannot go down in a smaller set. The simple idea is X faces less competition in T compared to S, then he should be chosen, more frequently in T.
So this implies the first condition, right? Probably.
Less
is more. This less is more, right?
No, this is actually satisfied by random utility.
Okay.
So this is actually a well-known condition.
I see.
And
okay. Yeah.
random utility got to satisfy this. Random utility satisfy even more, but
yes,
this is the kind of things. Choice probability cannot decrease when the set gets smaller.
I see. Yeah.
So I need to relax this. Okay, so that's what I'm gonna do. So our conditions that this needs to be relaxed, and it is actually, we call the U regularity. It's almost the same structure. That was the regularity. We put this U means upper contour sets, weak upper contour sets. So when I'm looking at the data, I cannot tell you that the frequency of X cannot go down. What I can tell you is the frequency of upper contour set of X cannot go down. So your intuition, less is more, comes from this upper contour set. Because I can improve my choices in the smaller sets. So that's exactly the reason you need to place just X itself with upper contour set of X.
Each element in the upper contour set, or yes?
No, this is the entire. So this notation says
I see.
the total. If you look at all the guys in the upper contour set and you sum them up, that number cannot go
for
up.
the whole set. I see.
Actually, if you take the best alternative, because the upper contour set is going to be itself, and then that guy will satisfy regularity. But for smaller, the alternative in the lower ranking alternative, actually you might be violating regularity, but not for the best guy. Okay, so this is a relaxation of regularity condition for lower guys, basically. Okay?
Yes.
Yusufcan, you have about 15 minutes.
I am good, I think.
Yeah, I thought I would tell you.
Whenever, I need to stop. I hate to going over it. And I think you almost get what I need to say anyway.
Yes.
So this actually could have been only axiom we need. It turns out that no, we need one more axiom. I want to say this one. Actually, in this world, regularity might be violated. especially for the worst alternative. I'm going to tell you actually with pictures later on, but that will be the case. And the next axiom is another generalization of regularity, and it's called the weak regularity. You don't need to read this one. What I want to say actually, the regularity says, if you look at this set, you know, this probability of X chosen in S must be smaller than for all T's. This condition says, look, it should be at least for some. Remember, the less is more has two conditions. The one of the conditions said that, look, you cannot make a crazy choices in the smaller set. So that's what I'm actually trying to capture. Indeed, less is more has two parts. If you drop one, essentially the second part, basically you need to drop this axiom. But otherwise you need to keep it. And that's it. That's the only two axioms I need. If you have these two axioms, then you give me the reference ordering. Then I need to check U regularity and the weak regularity. Then I will give you unique L-PRC representation of this. Uniqueness comes from the theorem 0. But this has a prediction power. And this two condition is actually very easy to check. If you have the data, it is a simple conditions to check. And the cool thing is identification is still unique. It got to be unique because even more general theorem was unique. Okay, so that's the improvement. But the first bullet line still is exogenous. So this might not be very attractive, especially if you are interpreting this as a preference. Even a single individual, how do I know his preference? That's the same question we ask. Can we do more? Can we infer also preference? And it turns out that actually we could, otherwise I wouldn't write this one. So what happens, the reference ordering is not given. Actually, I'm going to show that we could, but first I define endogenous L-PRC if there exists an ordering, which I don't know, but there exists an ordering such that this guy actually represents my data. So now the idea is how we can find this guy. This is actually this proposition. It gives you a hint how to identify the rank. So it says that, look, there is Y, and what this happens actually, the frequency of Y was higher in a larger set, but in a smaller set, it is actually smaller. And in this world, it says that X must be ranked above Y. So any regularity violations that I observe, this immediately informs us about the preference ranking that this model has. I think I have I'm going to skip this proof. It's not important. Any question?
You're good. Yeah.
Okay. So one assumption I'm going to make, assume that everything chosen with strictly positive, and there is no two-choice problem that X is chosen exactly the same probability. These are knife edges, and there is no finite data that actually I can verify those assumptions anyway. And I'm just going to assume away. And if that's the case, then we can actually uniquely identify a reference order. So the theorem basically says endogeneity, the preference is endogenously driven. So here, the choice type is actually uniquely identified. The probabilities are uniquely identified, and also the reference ordering is uniquely identified. So do I have like 4 minutes?
Yeah.
I want to show
yes.
pictures. I want to finish the paper, because I want to place this paper in the literature, and I want to do this with the pictures. So this is Bloch-Marshall triangle. What I'm using actually here, every choice is actually a point in that simplex. For example, choice from X, Y, Z, a point in this triangle, because I can choose with some frequency X, some frequency Z, some frequency Y. And the choice is this guy, because I only choose X and Y, that will be a point in that line. With certain frequency, I choose X, certain frequency, I choose Y. So for example, this part is going to show you pi. I don't know whether I'm going to be able to write this. But
yeah.
That actually show you the probability of X chosen and XY. So what I'm going to tell you here, I'm going to fix the binary choices. I'm just going to fix random points. And I'm going to tell you what this model actually predicts or allows for the tripleton choices. Random utility model says that your tripleton choice needs to be in this blue triangle. Okay, fixed in the binaries, random utility only explain this blue line. What about logic model? Actually, logic model, the loose model says there is no loose model in this world. Because the loose model, this dotted line needs to intersect at one point. Because I choose the binaries in a way that there is no loose in this world. There is a random utility, but not loose. So this is the single crossing random utility world model. This is actually is a point in this world. It's very high prediction power, but I'm sure that you can easily violate this model because it only predicts, given these binaries, you got to be here. Tripleton choice needs to be here. There is a econometric paper, Manzini Mariotti, is limited attention. Actually, in this case, they are also points, but in the random utility, because they are subset of random utility. Again, is a single point. Another econometric paper on random choice. This is actually a line. So we started with the points. Now, Brad-Rehbeck is actually the line. What about PRC? PRC everywhere. That's why I didn't write, because PRC doesn't make any prediction. It could be any place in that triangle. What about L-PRC? L-PRC is actually this red trapezoid, I guess. Okay, so that's the L-PRC. So what this says, Scrum is a special case of L-PRC. L-PRC has an intersection with RUM, but in a very knife-edge intersection. So these two models actually distinct from each other. And also it is distinct from both Brad-Rehbeck and Manzini Mariotti's limited attention models. And this is my paper on random attention. It also turns out that actually distinct from that model either. This is also kind of a generalization of random utility, but in a different way. And the last one is endogenous L-PRC. Endogenous L-PRC actually tells you that not only this trapezoid, but there are 3 other trapezoids. And if you are here, I'll tell you your preferences. If you are here, I know your preferences. If you are here, I know your preferences. So I can uniquely identify for each region. And I think I am done. I'm going to skip this. Do I have 1 minute?
Yeah.
Maybe not.
Yeah. Go ahead.
Okay.
Okay.
So let me summarize it. So what we did, we introduced this progressive structure. So why we need this? Because I want to study things that outside of utility maximization, and random utility doesn't allow me this. And that's why I need this. And you can actually study many different things. We studied the less is more, but you can study anything you want. And you can, what we showed, even the ranking can be endogenously driven. But this is, as far as I see, is just scratching the surface. There are many things needs to be done in this world. Any deterministic model that we have done so far can be applied now. Before I didn't know how to do it, but now we can actually, we can do it. And then I'm gonna be done. Thank you for your, attention.
Very nice, thank you.
Well, so, thank you, Yusufcan.
Thank you very much.
Thank you. Yeah. We'll have a little time for a few questions. So.
And I'm happy to answer it.
Yeah.
Yeah. May I? Yeah. Yusuf, I was thinking, well, at the end you said there are a lot more things can be done. I was thinking two things really. Within the choice framework, what if we don't have such a certain, I mean, I give you a data set and that you cannot do anything about it. The question is that the end of the world, or?
So you mean, you give me data, what type of data set you are giving to me?
Like your data set, but you, yeah, if you take, take a particular example from the literature, something that cannot be, what can you say when nothing can be done? Probably I'm not.
So
if it
let me go back to like the examples that actually I initially.
Yes, the very first example that yeah. Yes, this fails the.
So this type of things. My model actually captures all of them. But each model will have a specific structure. For example, reference dependence, when you study the loss aversion, like a Köse-Graben allows certain violations, the Whorf violations, not all. So what this does actually, it provides a restriction on the choice function that you will use. That will be complete, a subset of this model, but it's going to be more, the restricted. Or you can do willpower. Willpower allows certain, but not the other. Attention. Actually, I have two types of attention model. One allows one type of choice function, but not the other. So basically what I'm telling you, look, at this point, you can use any of these. Focus on any of these and then study. And the choice data, so your question is, what happens, for example, in the picture? Let me go back to picture and say that we say the L-PRC represent this region. What happens if you have a data point here? I know it is not L-PRC, it is not less is more. But I cannot tell you, maybe it's willpower. Unless somebody investigates willpower structure, it might be actually boiled down here. But what I know, it is for sure PRC because of the theorem 0. So there is such a model exists, but I don't know exactly. So the only thing that we investigate as of now, less is more, and less is more boils down to this. I mean, I'm sure that there are other models is going to capture other part of the regions. As of now, we only captures, less is more captures only this. But the good news, PRC captures all of them. So there is such a model, but we don't know it.
So I have one question to this endogenous L-PRC. Okay, so what is the algorithm, so to say, to determine it? For the exogenous, I have the reference order, and I look for the choice function that satisfies these conditions, right? For endogenous, I have only restrict to all LPRS that generate strict probability orders, correct?
Exactly. So
and then I'm looking what would be the reference order such that is consistent with such strict probability. How do you know it's? I'm a little bit lost. What's the algorithm to determine endogenous L-PRC?
Endogenous L-PRC, very good question. So remember, I assume U regularity. So this means that the best alternative got to satisfy regularity. Okay, so if you look at this picture, so in this blue triangle, every alternative satisfies regularity.
Yes.
But for example, if you come to here, I don't know whether you can see my, do you see a point right now?
Yes, yes.
Okay, so for this, if you have a data set at this point, what I know, regularity is actually violated for Y. Because in the tripleton, Y chosen is more heavily, but in the binary is chosen less. So this means that Y cannot be the best alternative. Okay, so this is actually the type of algorithm that you start. The Y cannot be the best. Actually, if I'm not wrong here, it should be X, Y, Z actually in this region. This is actually in the paper. Actually, we show how you can do it, but this is the kind of an intuition. I need to have one guy. Also, I try to actually tell you in the one of the this proposition. Once I observe a choice reversal, it tells me the ranking. That's how we actually use it. This is actually very similar to even deterministic worlds. In the deterministic world, all the bounded rational model use warp violation, reveal something about the model. Here is a regularity violation, is going to reveal something about the model. So it's sometimes actually like warp violation is something bad. No, for decision theories is a good thing. It tells you something about the model.
Sure.
Yeah, that's the kind of a idea that you use to review.
And of course, this set will be always larger, right? Of this data points that are endogenously rationalized.
Yeah, this is for three-dimensional simplex. Okay. I don't know how to draw you on the four-dimensional. So.
Okay, very nice. Thank you. Very nice.
Well, thank you very much, Yusufcan. Great talk.
Thank you.
Beautiful paper. Thank you.
Available.
Thank you very much.
Thank you.
Thank you and good luck.